So process control, manufacturing automation or production automation. Today's lecture on 3rd of November is about compensating of different imperfectness of the characteristic of the plant. We start with very high relative time delay, its origin, effect, and why it's necessary to compensate. Compensation of the plant time delay means that the plant model, which is first order time lag, this is the plant model, time lag and time delay. The ratio tau over t is greater than 0.5. This can be due to different reasons. Approximation, of course, because we have experimental S-curve and the model time lag with time delay in series gives this dashed line. As a result, they tend to join the two lines, the experimental and the model. But there is discrepancy between the characteristics, and for the time when this tangential line crosses the axis, this tangential line in the inflection point covers the linear part of the step response. So it crosses the axis, which is time, in a point from which to the origin is the time delay. So the time delay is the time for which the plant almost doesn't respond to the step change. Its response is after the delay time, like in the model. So it starts after that till it settles at this line, and the inflection line crosses this settled value, and when projected results in time delay, in time constant. So it's important to know the ratio, delay and time constant. This ratio went very big. This means for a very long time the plant doesn't respond to input change. It's dangerous because we get no information. After this time elapses, suddenly the plant gets very high response, the realistic response if we do not change the input. But input to the plant is the control action. And if the plant shows no response, the control action increases and increases. And the response of the plant when it appears after the delay will be respond to very high input and may cause very great increase of this settled value because the plant doesn't operate by itself. In a closed loop system, it is the controller in a feedback that controls the input. So the response of the plant to high input becomes very high, and it's possible the controller not to be able to eliminate this increase of the plant output. And the plant output may destroy the installation because the system will become uncontrollable. The real term is unstable. So the next reason is that we have a very long room, and the variable we control, for instance, temperature, takes different values and has different step responses at one and the same change of input. The change of input is hot ambient temperature in the cooled room during summer, And when this temperature is measured in different volumes, equal volumes, but the room is very long and it's divided into different volumes, within a volume we have one and the same step response. So θ1 is temperature in volume 1, temperature in volume 2, and so on. But these responses differ in adjacent volumes. This is because temperature depends not only on time, but also on space variable. Here only the distance is important, but space has three variables. So if we consider that within a volume we have time lag with time delay model, Ziegler-Nichols modeling of this step response, the parameters will differ from volume 1 to volume 2 to volume n, the final volume. So we'll have different tau, t, and gain. The gain was delta change of output per delta change of input. If the input change is stepwise, we study only the plant. The stepwise has a magnitude of this step A. So from initial to final value divided by A gives us the gain in the Ziegler-Nichols model. So delay appears of approximation, but delay may be result of distribution of plant parameters along the length or in space. So these plants are called plants with distributed parameters because the model, Ziegler-Nichols model parameters depend on time and also on space variable. So a distribution in space causes this delay because the hot air should mix first with this volume which is nearest to where it appears, and after that goes further along the length in this room. So it needs time. All processes that take place in installation have some transition related with inertia of flows. Mixing processes need time to well mix, temperature to become even. So these are delays result of the processes that need some time to take place. This is the delay due to approximation, and this is the transport delay. When you apply change of input, the step input is applied here, but after some time the conveyor leads this change to affect the level. So the control variable is affected after transport delay, which depends on the length of this part of the conveyor and the velocity of the conveyor. So three components are important. This distribution of parameter plants usually are presented by separate Ziegler-Nichols models for each volume. So we have in series several plants. So we have a plant of high order because the series connection of transfer function is the product, and the time lag element, the product of several time lag elements, means product of several polynomials in the numerator, and the denominator is responsible for the order of the plant and the order of the closed loop system also. So we increase the order of our plant by presenting space distribution by series connection of simple Ziegler-Nichols models. So the delay origin is now clear, and what we have is why should we compensate the relatively high time delay when it's greater than 0.1 or even 0.5, when it is greater than 0.5 or even greater than 1. All methods for tuning of controllers expect that this ratio is less than 1. When it's greater than, this means the delay is greater than time constant. Then we need some compensation techniques for this great relative time delay because it affects the stability of the system. The stability of the system is that has a criteria in the frequency domain, which means the Nyquist point on the real and imaginary part of the frequency response of the open loop. The open loop is the numerator, 1 plus open loop is the numerator of the closed loop system. So this denominator generates the roots of the characteristic polynomial. So one of the criteria for stability is all roots to have negative real parts to be allocated in the left half of the root plane where their real parts are negative. Or if we take the frequency domain, we need this open loop part not to cross the negative axis beyond the critical point stability called Nyquist point. And this is the Nyquist plot. Let's see first the plant. The Nyquist plot of the plant, not of the open loop, when we have only time lag model, is this semicircle. It is built for different frequencies. For substituting S by J omega, we obtain complex number with real part. For this point, this is the real part, and imaginary part, this is the imaginary part. So the imaginary and the real parts, or the magnitude and the phase counted from the positive real axis. So starting from here, we count the phase. So magnitude of this vector and the phase also determine this point. So each point is related with one frequency. This point is related or computed for frequency omega I. But you see this semicircle is located in quadrant 4. From here usually start all plants of high order, and they rotate to pass through as many quadrants as their order is. So a second order model, so 2 time lags in series is a second order model. Then the start will be somewhere at the real axis, the positive part, and it will finish in origin, but will pass through quadrant 1 and quadrant 2. So the influence of the gain of the plant is related with the radius expanding this circle, and this initial point will be to more positive values. So any gain change when increasing in the plant expands the characteristic. The same is valid for the open loop characteristic. What happens if we add the delay part? The delay part rotates this point so that bigger magnitudes are rotated, and at some critical, this is the angle of rotation. It depends on the delay. And for some critical delay, this Nyquist point can be reached. Or if we have higher gain, higher magnitudes can be rotated to a smaller angle to reach this Nyquist critical point. So because the time delay is not a rational function, it's not a ratio of two polynomials of Laplace variable S, it is transcendental. But in the frequency domain, it is exactly represented by cosine omega tau plus sine omega tau. So for different omegas, we can have a cosine and sine computed and substitute this frequency characteristic by Euler's exact representation in the frequency domain through cosine and sine functions of omega tau. So we use frequency characteristics to design controller in order to be able to exactly represent the time delay dynamic unit, which approximates high order distribution in space, all type of delays reasons for delay. They are simply represented. So this is first order model with time delay. This time delay rotates the original characteristics. Infinite number of quadrants are passing. So it is infinite order of the plant. So we increase the order to infinite. Finally, the dotted line tends to a circle, and many times in circles this circle. It never reaches the origin. This is due to the time delay. And the time delay makes this plant of a very high order, infinite order. When we use a controller, the open loop system is the one we judge using the Nyquist plot whether the closed loop system is stable. So if we add a controller to control a plant without time delay, this is our plant and this is the PI controller. The integrator in the controller, 1 over S, is integrator. This integrator changes the initial point with one quadrant. Instead of starting from quadrant 1, the open loop Nyquist plot, which is the product of frequency of controller and of plant, it will be this solid line for zero delay block. But you see, this is a second order system. And I said, if you increase the gain, either of control of the plant, because the product of these two will give us the open loop. So the gain is product of controller's gain and plant gain. So each of these gain, or both if they increase, we expand this graph, but you see it will reach origin and will never cross the negative axis, and it will never reach Nyquist point and beyond in it. So we can have a very great gain of the controller in order to be fast responding to all disturbances and changes of reference, to reach reference without any error. This integrator eliminates steady state error, but dynamic error is also reduced by great gain of control. So a second order system can use maximal possible gain of the controller, which accounts for the maximal error input to controller. If the error expected is takes values plus minus 10% or 20%, we can take the biggest possible gain that would not lead to saturation of the control action, because the control action is a signal in some standard ranges, for instance, 420 milliamperes or minus 10 plus 10 volts. So this top value should amplify the error and not reach these bounds at the output of the controller. So we take the biggest possible gain, and no way the system will remain stable, no way to disturb stability, to violate stability. So when we add the delay block, if the plant needs model with time delay and the time delay is very high with respect to the time constant, we'll obtain this snail shape of the Nyquist plot of the open loop system, which at some critical value for the time delay can make the system critically stable, or even unstable if this characteristic crosses the negative axis beyond the Nyquist point. So somewhere after this Nyquist point. So what is important that we have limited gain of the controller, which has to account for the time delay. So the greater the time delay, the smaller the gain of the controller. We cannot expand this characteristic that much. And at some very small gain, because the delay is very high, our control is not effective. That's why we need compensation measures for this high time delay. And there's a simple scheme, Smith predictor. The Smith predictor is using artificial feedback with the specifically designed transfer function, which encloses our standard controller. For instance, we have PI controller for CS, and we have to compute the feedback in a way to eliminate the presence of time delay in the numerator. So the closed loop system contains a plant with time delay, and it's present in both numerator and denominator, and we'll try to compensate through this feedback only the stability impact of delay, so the delay block in the numerator. So this is a standard closed loop system without the feedback. And when we put the feedback, the feedback controller is called Smith predictor because it predicts the behavior of the plant when the delay elapses. The time is greater than the delay. And this behavior predicted is properly accounted with the control action. Now the plant is part without delay and the time delay, but the feedback configuration of the controller, so the transfer function RS of the Smith predictor, is feed-forward channel transfer function and the loop transfer function 1 plus this series connection that makes the loop transfer function. So we substitute, when we have Smith predictor in series to plant, this is a closed loop system with respect to reference, and the feed forward is RS multiplied by the transfer function of the plant, and the loop is unit feedback, so RPO, the delay, 1 plus loop, because the loop transfer function is the same as the feed-forward channel transfer function, as we have unit feedback. So we do not change through the feedback the loop transfer function. So substituting R with this expression leads to different. The numerator is the same as if we do not have this feedback, but the denominator is changed. Here we see the feedback transfer function, and we'll try to compute it so that the final denominator has a characteristic polynomial, this one without the delay block. So the characteristic equation should be equal to this characteristic equation, and from this we'll derive the feedback transfer function. So the only unknown is the feedback transfer function. One from here and here are cancelled. C as the controller, PI controller transfer function is present everywhere after cancelling one. And the result is C feedback is equal to 1 minus the delay block, and in front is PO. So because 1 comes from this, when PO is in front of brackets. So 1, this part with minus PO in front of brackets will be 1 minus the delay block. So we need only the model of the plant to construct this feedback, and these points around the controller are accessible. You can measure the control action. This signal can be applied to the algorithm or the device, added as hardware as a feedback. And here is a summing element which can be combined with a summing element, comparing element of the controller, where the error is obtained as difference between reference and measured plant output, the output we want to control. So this feedback should rely on precise plant model and parameters K, T, tau. Now, using this feedback transfer function, our Smith predictor, we substitute this where feedback is present in the expression of the transfer function RS, and it becomes this way. So the approximation of RS often leads to a PID controller with specific parameters, which depend on the tuning parameters of the P controller and the plant model parameters. So let's explain how the compensation is accomplished. During the time delay, our controller should work with a smaller gain. Let's have proportional controller because it's easy to explain. And this is the feedback. Plant model without delay and parallel 1 minus the delay. This is a negative feedback. When we apply step change of error, the controller reacts with step change of output modified by the gain of the controller. So this dash line could be if we do not have this feedback to the controller. But with the feedback, what happens? At first, the controller responds with the control action, which is Kp multiplied by E, but then this output feeds a time lag, which with minus appears in this summing element. So time lag, it is the signal minus V, and time lag, but after the delay, so we repeat this reaction, but after a delay time, and because here we have minus and this is minus, minus and minus in series, the result is plus. So the blue, this line, this exponential growth shifted after the delay time is the signal W at this point, so taken with plus. So at this point, we have to sum these two signals to obtain the feedback. And this feedback is this sum is negative and then increasing at the steady state zero reaction. So the step change of error is modified by first decrease of this error, so multiplied by Kp decrease of this signal till the time delay, and after that we have some positive compensation of this violet line till the steady state when the magnitudes positive and negative are equal, so no more influence. So you see how the gain of the controller is adaptive. It's smaller for the time of the time delay and then returns to its normal value. So this feedback stops operating after some time when we have almost 2 times time delay. So for the time delay, when we need smaller gain of the controller to ensure stability, we have this adaptive smaller decreasing gain. After that, we have perfect behavior. We can use high gain. We'll obtain good compensation of disturbance and fast following changes in reference. So reduce dynamic error with high gain of the controller. So this is how the Smith predictor acts with adaptive gain And the idea of tuning of the controllers is modified. You cannot tune your PI controller using these engineering formulas we studied in previous lecture, but we have to account that the presence of the feedback is making the system characteristic polynomial a second order system, because the delay is no longer present in the numerator, and when we have PI controller and time lag, the system is second order. So second order system I showed you. The Nyquist plot is the solid line. PI controller with plant time lag without delay. The closed loop system, the open loop is this product, and the Nyquist plot, when S is substituted by J omega, gives this result for different frequencies. We can expand, so what we are going to do, use very high gain of our PI controller, considering only the range of input. So in our first laboratory, we assign gain of the controller 10, the top possible. Then we have a second order system. We can use one of the methods for tuning of second order system. I will revise taking lecture 2, and we started tuning first order system, second order system. So this is first order system, and here the combination PI with plant model time lag gives a second order system, and the possibility is to take to allocate two roots of the characteristic equation, one very far from the axis in the root plane, the other at distance, which is related with the settling time. Or we can have equal real roots, and that will ensure critical step response, only with one maximum over the reference and no oscillations, or underdamped process if the roots are complex conjugated pair. We use the characteristic equation to obtain the roots, and then if the discriminant is smaller than 0, so it's negative, we put negative sign and the imaginary unit here to make the square root of positive discriminant. So this positive discriminant with the numerator gives beta in the root, the imaginary part of the complex conjugated pair of roots, and this is the rest. This part is alpha. The real part, this is positive, and the minus shows that we ensure negative real part or stable system. If alpha over beta gives desired degree of oscillations, so the degree of oscillations is related with overshoot and other time domain performance indicators. So we select desired degree of oscillations, and the result is relationship between Kp and Ti. Kp is 10, so we don't need any other second criteria. So Ti is computed on the basis of the plant model, time lag model. parameters, the desired degree of oscillations, and the top gain of our controller. So this is important. If we do not use the highest possible gain, which allows us this feedback, the feedback cannot be tuned because it contains parameters of the plant model. Plant model is necessary to tune this controller to obtain the feedback, but we can tune the controller knowing that we can use a very high gain, which is not possible if the system contains time delay in the numerator, or the plant is with very high time delay. We need the feedback first, and then we can have very high gain. So if the plant changes with respect to the model which is put as feedback to controller, we will have worse performance of the closed loop system. So it's important to have to be sure that the plant model is precise and the plant doesn't change its characteristic with time or under different influences. So the high gain ensures very short settling time, the high gain and the feedback to control. So the Smith predictor is more effective when we properly use the possible high gain of the main controller, the standard PI controller. If we use Smith predictor, this is the step response when we change reference, and after some time or settled initial value, we apply step change in disturbance, and again the step response settling time is up to here. From here, when we apply step change of disturbance to here, we measure the time. This is the settling time. Without this feedback and the high gain, we'll have very small gain of the ordinary PI controller when the plant delay is very high, and oscillations for this small gain not very effective. The dynamic accuracy is bad. The settling time starts from here, the delay. This delay is related with the presence of the time delay in the numerator. So we compensate with feedback only the numerator. So we try to get rid of this time delay, but this is preserved. That's why the step response has initial time delay from change of output. So from here till settling, so practically equal to reference of the output Y. This is the settling time. So it's, let's say, 5 times greater than that of a Smith predictor. And during the set and this time, when we have difference between reference and output, so we have dynamic error, this means that the process inside behaves not in a normal way. So the production can be even with low quality. So we have to reduce these oscillations, reducing settling time, maximal dynamic deviation, both with respect to change of reference and with respect to disturbance. Here we use negative step change of disturbance. That's why output starts to decrease with again settling time of Smith predictor system 3 times or 4 times smaller than without Smith predictor. In our laboratory, we'll compare single input simple system with pit controller tuned according to the same criteria, but a second criteria is required usually. The gain Kp is limited. And comparing its step response with respect to the two possible inputs, change of reference or change of disturbance. The step response of ordinary system is compared with the system we investigate, which has additional controllers added to compensate some imperfectness of plant. For instance, the high time delay in the case of Smith predictor. Now we'll continue with the lab, and after the lab, we'll have still more of the lecture. So I'll stop recording because the lecture was up to here. That was not here. Yes. This is first part of our lecture.